Great. Okay, awesome. So I'm going to go ahead, but I'm going to warn you, my internet connection sometimes gets a little bit flaky. In that case, just please let me know so I can turn off my video so for better quality. Okay, hi everyone. My name is Saeed Amizadeh. I'm from the Applied Sciences Lab at Microsoft. And today I'm going to talk about a general approach for constraint satisfaction solvers, specifically SAT solving, that we termed as PDP, which stands for propagation decimation prediction. But the purpose of this talk is mostly talk about the high-level ideas, and this methodology is going to be just one example of the whole story. So I'm coming from a machine learning community, and my general interest is how signals and symbols interact with each other in deep learning. And specifically, I'm focused on neurosymbolic methods, which aim at augmenting traditional deep learning methods with the power of symbolic calculation. So more recently, I've been focused on neurosymbolic visual reasoning for machines that can look at the world and do logical reasoning and differentiable first order logic. But in the past, I've also worked on neural SAT solving, which I'm going to talk about today. So in the ideal world, as we saw by now, we have this magical solver that given a problem, it can give us a solution. And for the sake of this talk, we can think about the problem as a CSP. And of course, this problem is coming from certain distribution. And the reason that this solver is magical is because no matter what distribution your problem is coming from, it can still provide a solution in a reasonable time. And of course, in reality, we don't have such a magical solver. Instead, for different distribution of problems, for different problem classes, we usually come up with these different algorithms, different solvers to give us solution. Now, what if we could, instead of doing that, we could simply train a new solver for a new distribution? And furthermore, what if this trained model could pick up solving strategies that probably were overlooked by human algorithm designers? This is what I call the allure of machine learning. This is what machine learning ideally promise, that you have these machine learning models that you can just simply train on a new distribution, and maybe for some other distribution you have another framework that works better, but still it's better than having one model per each distribution. Okay, so I'm gonna quickly, skip over this slide because everyone in this community know what CSP and SAT is, but I'm just gonna give a, the way that we represent the SAT problem in this talk is through a factor graph representation, where we have a node for each variable and a node for each constraint, and a variable is connected to a constraint if it participates in that constraint. And each constraint is represented as a Boolean function, where it returns 1 if the constraint is satisfied, 0 otherwise, and it's defined on a subset of variables. Okay, so let's talk about the neurosymbolic approach. So in the old world, we have this classical machine learning models. We also have the classical solver and classical symbolic methods, and each of them has their own benefits and disadvantages. So classical ML can do learning and soft computing, but it cannot understand discrete structures. Unfortunately, most of the machine learning models work on continuous vector spaces. And it is not necessarily a scale invariant, meaning that if you train your model on the problems of certain sizes, it does not necessarily generalize to the problems of bigger sizes that are coming from a similar distribution. Whereas a classical solver, it cannot do the learning in a machine learning style of backpropagation or in a continuous space or soft computing, but they can understand symbols and discrete structures pretty well. And they are typically scale invariant, meaning that once you know how to solve a problem, you can still solve a larger problem. Probably it takes longer, but your search strategy is still valid. So really what we want to do, we want to combine the goods of the both two words together into this neurosymbolic approaches. So we can do this combination two ways. The first, which I call approach A, is we start from a machine learning model and try to make it understand discrete structures. So what this means is that I have this discrete problem structure. What I can do in the classical ML, I can manually extract some informative features that I think are important and give it to some machine learning model, some classifier, to produce a solution for me. This is, of course, the classical ML approach. More recent approach, which is a deep learning approach, where we, instead of manually design this feature extraction, we do representation learning. And we learn this, stack of machine learning end to end. So, and I'm going to actually talk about the second approach, which is deep learning, which is more exciting and more hot. Okay, so, and I'm going to give you two examples of the approach A. The first example is the famous Neurosat approach, which came out 2 or 3 years ago. And really the idea in Neurosat is basically we want to learn the structural patterns in the factor graph representation of a problem that can predict satisfiability for us. So it's a binary classification problem. And in order to basically learn the features, they propose to use a graph neural network, which I'm not going to get into the details of it. So that's one approach here. And the second model that I want to talk about is the work that we did actually 2 years ago, and this is called neural circuit solver. It basically learned to solve SAT problems for circuit problems. And the intuition is really that circuit has more useful structural signals in it compared to a flat CNF. And to do that, we devised this new form of neural networks, which we call directed acyclic graph neural network, because a circuit can be represented as a DAG, and the details of it is, of course, in the paper. And but what makes it very different from Neurosat is that instead of actually trained to predict satisfiability, this model is directly trained to solve SAT problems via energy minimization, which I'm going to talk about later during this talk when I talk about PDP. And this is the DAG neural network. Again, I'm not going to talk about the details of it. The details are in the paper, but this is the general architecture. Okay, so what's the pros and cons of approach A? The main benefit of approach A is that it's generic approach, meaning that theoretically, I have this beautiful black box neural network that I can just train on any distributional problems, and theoretically, I can solve any problem. The problem is that in practice, that's not going to work like that. And the reason is because this methodology of approach A completely ignores many of useful inductive biases that are present in classical solvers that we can transfer from. Instead, we basically force a machine learning model to learn everything from scratch. And of course, there is no guarantee that we can generalize to larger scale problems, and which is problematic with approaching. So with this, let's move on to the next set of approaches, which I call approach B. Approach B is, instead of starting from ML model, let's start from some classical solver, from some classical algorithm, and instead try to make it incorporate machine learning components and deep learning components. And for this, I give the example of what this talk is going to be about, which is the PDP method. So PDP method belongs to this group of approach A. And what it does is basically it takes the classical message passing solvers, which are based on the idea of probabilistic inference, and does this magic, which we call the neural relaxation, to turn it to a neural version, which is basically PDP. So before that, let's talk about briefly talk about the message passing ideas based on probabilistic inference for solving SAT. So solving SAT can be reformulated as a probabilistic problem in a sense that if you give me a factor graph representation of a SAT problem, I can generate the factor graph graphical model equivalent to that representation, and define a probability distribution over the variables as the product of potential functions, which are directly derived from the constraint functions. And you can easily show that if there is a instantiation to these variables that is satisfiable, it maximizes the probability. And so basically your problem is reduced to maximizing this probability to find a satisfiable solution. And the way that, of course, we do probabilistic inference on graphical models, one popular way is through message passing. And the way that message passing works is basically we pass these messages between variable nodes and constraint nodes on the graphical model, and such that the outgoing message from a constraint node to a variable node is defined as a function of the incoming messages to that node, and also the outgoing messages from a variable node to its constraint nodes are also defined as a function of incoming message to that variable node. And these two functions are basically can be anything. That's why we call it generalized message passing algorithm. And so this is the first step. So we run the first step until the message passing basically converges. Once the message passing converges, we can pick one variable based on some certainty criterion, let's say x1, and set its value to some polarity spin based on some other criteria. So for example, we take the variable x1 and set it to 1. And once we do that, we can of course simplify the factor graph and then repeat the entire process again. So, and this process is called sequential decimation. And once we do that, eventually, we have a value for every possible variable that we have. So this is, of course, a generic template because you can, F and G are not determined here. And based on the choices of F and G, you can have different algorithms. And all of these famous algorithms like Bleak propagation, max product algorithm, min sum algorithm, warning propagation algorithm, and survey propagation algorithm, these are all special cases of GMP. Okay, now that we know what GMP is, now let's look at how we can do neural relaxation to arrive at PDP from GMP. Okay, in GMP, the messages are basically a scalar on the real axis. Whereas in a neural relaxation, we can think about a message to be a vector in some high dimensional space. In GMP, the decimation runs only after message passing is converged. In neural relaxation, we don't need to have this constraint. We can have decimation and message passing to run concurrently with each other. In GMP, sequential decimation affects only one variable at the time. In neural relaxation, we can think about all variables can be affected at the same time. In GMP, decimation is defined as fixing a variable to a certain value. In neural relaxation of it, we can define a neural decimation as transforming messages in a stateful manner. Okay, let's get into more details of step by step. So what we propose here is propagation decimation prediction method, and the first step of it is propagation. So the first step is very similar to message passing in the classical algorithm. So we have these messages, except that the functions that we have here for message passing, they are neural networks with parameters that we can actually learn. And these neural networks are stateless. They're basically feed-forward neural networks. So this is the first step, which is for propagation. The second step is decimation. And decimation is simply defined as the interception of the messages that are coming from the propagators and apply a stateful transformation on them using two neural networks here. And we use, because we want it to be a stateful, we use recurrent neural network for decimators, which again have parameters that we can train. And really, the reason that this decimation is stateful is because the decimation, the classical decimation is a stateful operation. Once a variable is decimated, it stays decimated. No, we can actually generalize that to the continuous space and just apply some stateful general transformation to it. Okay, the third step is the prediction. The prediction is basically predicting a soft assignment between 0 and 1 for a variable based on the incoming messages that are coming from the decimator. And this is again defined by some neural network that has some parameters that we can train. So if we put everything together, and let's say I have a very simple toy example here. This is my CNF problem, and this is basically represented by this factor graph. This factor graph, when we have a neural equivalent of this, it's going to look like this. So we have propagators here, the square boxes, and then we have the oval boxes, which are the decimator functions, and then we have the yellow boxes here, which are the prediction functions. And these are all trainable neural networks. So this whole architecture now can be trained end to end. But the next step is we need to define what training is, what is our loss function, basically. So what we propose in this work is unsupervised training, and using what we call as discounted accumulated energy minimization. And this is very attractive because it is completely unsupervised. We don't need label examples. We can just generate examples in memory or use some unlabeled examples and learn from unlabeled examples. The way that it works is we define an energy for a given assignment as the minus log probability of that assignment. And the only difference is that here we replace the original potential function with some differentiable surrogate. And I'm not going to get into the details of it. The details in the paper, you can look at the math details of it. And then the loss function is defined as the discounted energy functions of that example over time. And the reason that we have this discounted, basically discounted factor here is because we want to encourage the model to find the solution fast. Okay, so I just need to do this checking. Is everyone still can hear and see my slides?
I can hear and see.
Yeah, looking good.
Okay, great. Okay, so and once we have this, we can train this model end to end from all the way from the label from the solution all the way back to all the parameters. So it's obviously a dynamic neural network. So the next things that I want to talk about is parallelization and batch replication. One benefit of these neural approaches, especially PDP, is that we can run PDP on multiple problem instances at the same time in parallel by simply concatenating them and pretend that they are basically one big factor graph. So we can solve a bunch of these problems at the same time on GPU. This is a very important benefit of this type of methods. But also, even in the case of if I only have one problem, we can replicate that one problem multiple times, making sure that each replica is instantiated with a different set of initial messages values. This way, we can search the search space, different parts of the search space at the same time in parallel. We call this technique batch replication, which is a very powerful technique, as I'll talk about it later. So with this, I guess I'm ready to show some results. So for this experiment, what we have compared 5 different methods. One is the Neurosad method that I talked earlier. The other one is, of course, our method, PDP. And the other method is a classical survey propagation method. And the fourth method is the reinforced method, which is, you can think about, it's similar to survey propagation, except that the decimation is not sequential. It has a concurrent decimation. And then there is the famous, of course, glucose method, which is an industrial solver. And so for the first experiment, we have compared these methods on random KSAT problems, uniformly random KSAT problems. And we compared them for different levels of difficulty. And the way, of course, the standard way that people define difficulty is by the ratio of the number of constraints that we have over the number of variables. And for each ratio variable, we have generated 500 random examples of 4 SAT problems. Each has 100 variables. And then we set so these are pretty small scale problems. Then we set, the maximum number of iterations for the iteration-based methods to be 1,000. And that would roughly equivalent to setting like a 3-second timeout for glucose method. And this is the result that we got. Unfortunately, we could not really train the neurosat model for any problem instances that were more than 20 variables. And so we only trained it for 20 variables, and it did not really learn anything for problems with 100 variables. But there is still more room to investigate why neurosat does that. One part of the problem with neurosat is that because it's trained to predict satisfiability, it has a very strict regime how to put a training data together. And the details of it, actually, the others mention it in their paper. So I refer you to there. But compared to the classical survey propagation reinforced method, our method, of course, performs much better. And sorry, the y-axis here shows the percentage of the problems that we could solve within the time limit. Of course, our method is doing much better compared to the classical method. And according to this graph, our method actually comes very close to glucose. It's almost similar performance. And this may give the impression that actually we are beating glucose or doing on par good with the glucose. Of course, this is not the case. And the reason is because here we put a timeout limit for glucose. So in the next experiment, we try to remove this time limit for glucose. Also, we make sure, so we basically let glucose to run until it finds a solution. And also we make sure to compare it against a serial version of PDP, which does not use parallelization. And also a third candidate, which is the serial version of PDP, plus batch replication that I talked about. And as you can see, of course, according to this graph, the top graph shows the number of problems that we could solve for different values of alpha, whereas the bottom graph shows the average time that we spend on each example. And it's clear that glucose wins all of the methods by good margin. But what it is interesting here, that the batch replication idea seems to have a significant basically impact on the number of problems that we can solve. And if you can think about it, batch replication here, what it tries to implement is the classical notion of restart, that we start the basically solution, the solving process from a different initial values, except that the batch replication does it in parallel, which is a very powerful thing. So in this sense, you can see that, of course, our method cannot beat glucose, but still compared to the original classical method, it's doing much better. So the third experiment that I would like to talk about is one thing that we talked in the beginning of the talk. A big promise of machine learning is the ability to adapt to a new distribution. And also one can argue that in many real case situations, we are not actually dealing with uniformly random SAT problems, but rather with problems that have inherent structures in them. So in this experiment, what we did, we experimented on pseudo-industrial random k-SAT problems. In a specific, the SAT problems that have a modular structure. And in order to generate the problems that have this structure, we have used the community attachment model, which is a very beautiful model to randomly generate this type of problems. And what we did here is we train a new model, which we call the PDP modular, on the modular problems, whereas we also and compare it to the model that we trained before on the uniform problems. And of course, and then we compare these two also with the glucose. Of course, glucose wins everyone here because glucose is famous to be able to solve this problem and this type of industrial problems very efficiently. But between our modular method and our original method model, we can see the modular the modular model beats the original model significantly with a significant margin here. And this shows that even though this type of message passing algorithms are famous to be doing well for random problems, even in that case, we can still train models that on a new distributions that can still do much better than the original model. So this shows this ability to adapt, which is one of the big promises of machine learning in this case. Okay, so with this, let's conclude the talk with some insights and takeaways. So obviously, we are not making any claim to perform on par with industrial solvers at this point, but we have some interesting insights that can give us some intuitions how to design future models. And I really want to discuss this with you and hear your feedbacks, because I think this is something that we can all discuss and talk about. So the first thing is that ML approach, as we discussed, can provide a generic solution framework that can adapt to new problem distribution. And this is something that we need to keep in mind. That's probably the main benefit of having machine learning over there. And of course, the other benefit is that machine learning can potentially pick up search strategies that are not visible to the human algorithm designers. So, and this is another, especially with deep learning, this is another benefit of this type of methods. So within machine learning approaches, we also argued that approach B is superior to approach A, and it's mainly because we can encode informative inductive biases from the classical models into the neural model, as opposed to let machine learning model learn everything from scratch. The other idea that we discussed is, and it's I think this is one of the most important points of this talk, is the idea of neural relaxation, how to move from some classical approach to a neural version of it. And this is very important because it gives us a tool to be able to design a framework that is neural and classical at the same time. And it is important to we have this relaxation, because we don't want many of the greediness of the classical methods that may end up performing some greedy search strategy to be transferred to the neural method. So we want to relax, give the neural method some room for learning better strategies. And the other idea, of course, is PDP here that we discussed here. It's really a general template that can implement the fully neural network, as we discussed, but it can also implement hybrid models. So the hybrid models are, for example, you can think about a model where the propagator is neural, but the decimator is classical, or vice versa, or any combination of those. Actually, the code that we have released for this work, you can have all of these combinations. You can try out all of these combinations. And the last point here is that, of course, PDP and generally these neural methods are highly parallel, and you can implement ideas such as batch replication. So with that, let's think about some of the general directions, important directions ahead for the future work. And of course, one thing that discussed so far in this during this workshop is approaching other aspects of SAT problem via ML. For example, providing proof of unsat or predicting the unsat core. These are all interesting problems that we did not focus in this work, but I think these are interesting works to focus on. But this point actually is I like this point a lot, and I think it's very important, is we really need to think about how we can incorporate classical techniques such as backtracking. So backtracking is a very important and powerful technique. How can we bring that technique to a neural framework such that we can satisfy two criteria? One is to keep the model still differentiable end-to-end, and make sure that we can still give the machine learning framework to learn something useful, as opposed to force something that is completely greedy to it. So with that, at the end of the day, ideally we want a generic neural framework with the right balance between machine learning components and powerful classical techniques that we can train in an end-to-end fashion. And that means that we need to really think about differentiability of the components of our solver. With that, I conclude this talk. I would like to thank my co-authors on this work, Sergey and Marcus. Both the paper and the code are available online, and you can also always reach out to me via my email if you have any questions. But thank you. I would love to answer some questions. Thank you.